Okay, so standard position. So let's go to the top. I know you guys are filling out the stuff. We'll come back to it later. So as you guys know, trigonometry, right triangle geometry, it's a big deal in calculus. So we got to just make sure we have a proper discussion. First of all, drawing an angle in standard position. Hopefully you guys know it starts here. We always start here. So it lies on the positive x-axis. We know this, right? The terminal side is where we end it, right? That's why it's called terminal. Now, counterclockwise, is x there positive or negative? Good. Thank you, Marie. Clockwise is negative. Thank you. So, for example, if I were to rotate an angle like this, if you were to kind of just guesstimate, what would you say that measure would be? 100 and maybe 120, 130, I don't know. But you get the idea of how to draw it, right? If I were to do something like this here, what do you think that would be? 360 twice, so 720, correct. If I were to do this, what do you think that would be? Okay, cool. Okay, good. So yeah, so we spin around multiple times. That could happen. So not restricted to 0 to 180. You guys know that rather angles can have positive and negative measure. Positive measure results from rotating counterclockwise and negative clockwise. Okay, so we're cool there? Good. Let's keep moving. And again, it's recorded so if you ever want to watch it. Co-terminal. So just so play on words. What does co mean? Together, right? Like a co-captain or co-pilot. Terminal sounds terrible, like ending, right? So ending in the same place, right? Like you have a terminal airport, where the airport ends, right? You go on the plane, leave. Or if you have a terminal illness, that sounds terrible, you die. Okay. Hopefully you guys live long lives. But yeah, co-terminal means ending in the same place, right? So if we look at 120, so let's think of angles that could be co-terminal. Like for example, if I do this, so the red is obviously 120. What's the blue going to be? Perfect, good. Love it, negative 240. Or I'll do green. If I decide to go around once and then back to the same place. So going around once and 120, what's that going to be? 480. Yep, you guys got it. So pretty easy, right? Okay, let's keep on moving. Radians. Are you guys comfortable with the conversion for radians? Okay. And if some of you guys have already taken the ACT or SAT, they do ask that, so you probably already know the conversion. Conversion is pretty simple. There are 2 pi radians, 1 rotation of a circle. Does anyone know what 1 radian would be approximately equal to 2 degrees? So know the approximation. It's all right. Don't worry, I know it. 57.7 degrees. I'll explain why in a moment. But 2 pi radians, 1 full rotation. So we know that's 360 degrees. So wouldn't pi radians equal 180? That's correct. We know this. So pi rads equals 180 degrees. We know this. Now, let me explain why radian exists the way it does. In case this is something I just like to do because I like doing it. You don't have to write this in, just sit back and relax. But back in the day when you guys learned geometry, say for example, there were like 2 and 2. And I asked you to find me this length. How would you find that length? What would you do? Go, Marie?
Do the central angle.
Yes. Yes. What's the circumference here? Correct. 4 pi, 2 pi r, right? And 90 is 1/4 of 360. We know this, right? It's proportional reasoning. That's all you're doing. So that's just got to be pi. So there's like a formula for it. Like, oh, I forgot the formula too. Like, that's nonsense. Just use proportional reasoning. I know this pi. And what's pi roughly as a number?
3.14.
So this is a length of 3.14. Okay, great, whatever. Now, what if I reduce this angle and bring these two radii close together? Can this arc be the same length as a radius? Can this arc be a length of 2? Sure. Why not? I can make anything I want, right? As long as I don't exceed the circumference. So I can reduce that angle and make it the same length as a radius. So when that happens, so like if I have a, draw no circle here, and let's say I bring that angle in a bit, I could totally make this length of r, and that's r and r. When that happens, when the radius equals, so this is actually, may want to write this down. When the arc length equals the length of the radius, the central angle has a measure of 1 radian. That is how a radian is defined. Okay? It's defined like that. So it's just something we accept. So radian is defined as when the arc length equals the length of the radius. So if I call this theta, you guys know about the Greek alphabets, right? Theta, all the other stuff, right? We're good at that. Cool, right? So theta equals 1 radian. Now this is where I use some proportional reasoning. A full circle is how many, what's the distance of a full circle in terms of r? 2 pi r. And how many degrees is that? Good. And over here, so essentially, and then also for the arc, that's 1 radian, and that's r. So if I compare full circle to 360 degrees and the arc to 1 radian, would you agree those ratios have to be the same? Yeah, that makes sense. Full circle is 360, arc. Well, the full circle is 2 pi r. That's 360. The arc, what was the length of our arc again? R, right? And then that's just 1 rad. What happens if I cross multiply? What do you get? 2 pi r times 1 rad equals 360 degrees times r. Does that make sense, what I've done so far? What happens to the r's? What are you stuck with? 2 pi radians equals 360 degrees. That's why 2 pi radians equals 360 degrees, for that reason alone. So then you can reduce it and say pi equals 180, or pi over 2 equals 90, and so forth. So a little rapid fire, but does that make sense how a radian compares to a degree? We see that now? Good. Okay. So, yeah. Well, yeah, we should talk about this. On a unit circle, remember x is horizontal, y, well, like any coordinate plane, x is horizontal, y is vertical, and SOHCAHTOA. So that's the basics. SOHCAHTOA. There are different acronyms you could use to help you remember that. Someone actually had a really good one. Silly old Hitler crossed something. Hold on. It was something with Hitler. I'll come back to it later. Um, I'm messing it up now. Sorry. Or you could say, way I learned in 6th grade, Oliver has a heap of apples. OHAHOA. I don't know. You can have your own ways. Um, I'm gonna come up with the Hitler one. I'm gonna come up with it later. Anyhow, okay. So sine theta is x over 1. Sorry, y over 1. So cosecant is 1 over y. Cosecant is the reciprocal. You guys learn about cosecant, secant, and cotangent. You guys familiar with that? But you guys have them in the graphs from. That's gonna be new. Secant is 1 over x. Cotangent x over y, and of course these are x over 1 and y over x. And the reciprocal identity is 1 over sine is cosecant. So 1 over cosecant sine theta. 1 over cosine is secant. 1 over secant is cosine theta. That's cotangent theta. And that's tangent theta. Okay, all's good? Sweet. Let's keep on moving. Now here, I'll show you the filled out one. I got it right here in my Algebra 2 honors folder. I used to teach that class many years ago. Kind of crazy I have all this memorized. I've been here a long time. I was much younger then. Yeah, I was single, didn't have kids then. So, all right. So anyhow, you have that. So hopefully you guys are comfortable with how this is set up. So we start on the positive x, go counterclockwise, 30, 45, 60, 90, just keep going. The radian conversions, what I usually like to do, think about what I love about you guys, because I can do this quickly. But 30, you guys see how 30 is the 6 of 180, so it makes sense it's pi over 6. See how like 45's a fourth of 180, so that'd be a pi over 4, 6 is a third of it. So that's pi over 3. And then notice that 120 is double 60, 2 pi over 3, 135 is triple 45, 3 pi over 4, 150 is 5 times 30, 5 pi over 6. Of course, keep those all the way around and getting all those other angles. And if you were to measure, of course, like using a protractor, some of the angle measuring device, 30, 45, 60, and so forth. In terms of the coordinates, how do we get those coordinates? Where does that come from? What kind of triangle are we talking about here? Yeah, go Laura? Correct. Yeah, good. Yeah. So you do have to have that memorized. So for example, the radius is 1, of course. Why do we call a unit circle? Because the center's at 0, 0, and the radius is 1. So this would have to be x and y, because x is horizontal, y is vertical. But if that's 30 degrees, and that's 60 degrees, isn't the side opposite 30 half the hypotenuse? So that's half. And if I do Pythagorean theorem, I should get x, which is root 3 over 2. Or it's root 3 times the shorter leg. Right? Because remember those ratios. By the way, on the SAT, they give this to you. They don't on the ACT, in case you're curious. So sorry, that's kind of messy, but you guys get the idea. So they could do likewise for this 60-degree angle, and the 45, 45, 90, it's isosceles, so the legs are the same. But if the hypotenuse is 1, then you should get something like this here. 1 over root 2, 1 over root 2. So we're okay with that? All's good? Okay, my handwriting sucks. I apologize. And that does that does rationalize as root 2 over 2. And how do you get all the other coordinates? Well, x must be negative over here, x y negative here, y is negative here. So then we have to apply this for evaluating trig functions, which we'll do in a little bit. ASTC, all trig functions positive in the first quadrant, only sine and its reciprocal cosecant are positive in the second quadrant, tangents positive in the third quadrant, cosine positive in the fourth quadrant, all senior state calculus, all sophomore state chemistry, as always mnemonics you could use to help remember that. In terms of the table, I mean, if you guys have fill out, cool. If you don't, I'm not too worried about it. Honestly, I just want to keep you guys busy while I was talking to Kingston, so we'll just move on. Reference angles. So a reference angle is basically an acute angle. Um, formed by the terminal side and the x-axis. Excuse me. Thanks. And the x-axis. So it's an acute angle formed by a terminal side and the x-axis. So if I have something like this here, and it's for 140, okay, that's terrible. Let me do that again. Third time's a charm. Because say it's negative 150 degrees. The terminal side is, of course, right here. It has to be an acute angle. So what would be the measure of that angle? So you refer to 30 degrees in the first quadrant. 30 degrees, the coordinates were root 32 comma 1/2. So let's expect these coordinates to be similar, but make an adjustment for x being negative and y being negative. So that's what we call a reference angle. It's acute angle formed by the terminal side and the x-axis. Yeah. So 120, the reference angle will be 60, right? We know that. And you can do likewise with radians. Also, you guys should be familiar that cosine is like x, sine is like y. We already talked about that. Yeah, I'll just move on. I'm just gonna jump around. Let's go to page 6. So negative 3 comma 4. Now in this case, the radius is not 1. So I've had some students in the past, and this is kind of the annoying thing with trig is that they just memorize, oh, Mr. E, you said x is cosine. Like, no, dude, you don't get it. Cosine's a ratio, right? Sine's a ratio. So of course that's the length of negative 3. That's the length of 4. What's my hypotenuse? So my sine would have to be what? My cosine? My tangent? Got it. Cool. Okay, now for example 2, what quadrant am I in? 1, 2, or 3, or 4? Yep. Yep, because tan's positive, but sine's negative. Opposite over hypotenuse. So my opposite's -2, my hypotenuse is 3. Never make the hypotenuse negative. It's always positive. But -2, because you're pointing down. Using Pythag, what's the length of my horizontal leg? Root, but make it negative. So what would cosine be then? Okay. Oh, 3. Yikes. Cotangent is now adjacent over opposite. So if you do opposite over adjacent, I get -2 over -√5, but it should be √5 over 2. Gotta get A over O instead of O over A. So √5 over 2. So the homework you guys will have tonight will be kind of stuff like this. Just reviewing, making sure you guys are comfortable with all these things. Should be pretty straightforward. And more I think about, there's a lot of busy work here, so I'm gonna cross some stuff off. I don't like this busy work. So anyway, I'll tell you that I'll get the homework in a moment. Yeah, it's too much busy work here. Okay. Yeah, so you have stuff like this. Let's keep on moving. Yeah. You get the idea. We'll skip example 3. Let's look at example 4. Okay, do that one, sure. And we'll do example 5. What would make that true? You want the y coordinate to be √3 over 2. What angle in radians would that happen? Pi over 3? Or if sine's like y and y is positive, so first quadrant and second quadrant, what's the equivalent angle in the second quadrant? 2 pi over 3, perfect. If secant is -√2, that would imply that cosine theta is -1 over √2. Or -√2 over 2 if you rationalize the denominator. Okay, so yeah, I can like draw and like do SOHCAHTOA, but ultimately we got it fast. We got to do quick, right? So cosine's x is negative, so we're clearly in the second or third quadrants. And if you want negative root 2 in terms of radians, where will that happen? And 5 pi 4, good. Gotta be fast like that, good. But I would just take like over a month to cover my algebra 2 class or LO pre-cal, so we're doing this fast. But you guys see this already. Okay, now we're getting the graphing. You guys should be pretty comfortable with how the graphs of sine cosine look. So cycle is what's the right way to say this? It's like one wavelength, I think. That's probably a way to think about that. One wavelength. Period is the length of one cycle. Like, now we're back to our normal schedule, so our periods are 60 minutes. Periodic function repeats itself. That's what sine, cosine do, and all the trig functions. Amplitude is from the middle to the peak / trough. The trough is the bottom part. Key points. We have our max. We have our min. And I don't know what we can call these. We can call them the middle. What do you call that green line? Amplitude, perfect. Good, okay. What do I call this right here? The period, right? Okay, any questions? All right. So if I graph sine for you guys, it's gonna look like this. And essentially, what am I doing? I'm taking the unit circle and, like almost unraveling it, where I'm taking those points. I'm taking the y coordinates from the unit circle and plotting them. What do you think my domain is? Range. Then 1 to 1. Period. What kind of symmetry? Odd or even? Now you guys know what that means. Odd. Yeah, that's because sine negative x. That's an identity we'll talk about in a couple weeks, or but next week, I think. Equals sine equals negative sine x. That's true because on the unit circle really helps explain everything. Sine of 30 degrees equals negative sine. Sorry, sine of negative 30 equals negative sine 30, right? Because sine 30 is 1/2. So negative sine of negative 30 is also 1/2. So we expect that to happen. X-intercepts, obviously it's going to be, we like to say it's n pi, where n is any integer, or k pi, somebody use k, and y-intercept is 0, 0. All's good? All right, let's keep on moving. There are no discontinuities, no asymptotes. So that's none, none, and none. No, no. Cosine works the same way. Starts at the peak though, because cosine of 0 is 1. How's it shifted compared to sine? By pi over 2. That's why it's called complement of sine. Complement angles after 90 degrees. Negative theta theta. Range, -1 to 1 still. Period still 2 pi. Symmetry? Even. Now you guys know. X-intercepts, I'd say k pi or n pi over 2. Where n is any odd integer. Y-intercept is 0, 1. Absolute max. It's always going to be a value of 1 and an absolute of -1. Because remember we talked about relative extrema, right? Absolute is the highest possible point, and there's a whole bunch of absolute extrema. They're everywhere. It's infinite. And the absolute, mins and maxes, right? Any discontinuities or asymptotes? No. Yeah, I forgot to have an absolute maximum for sine, but it's the same thing. So, okay. So I'm gonna really jump around a little bit here. Let's go to page. And if I feel like we have to come back to this, we will, if I feel like we need to. Let's go do a couple more examples and I'm gonna be done because I think you guys know what's up. Let's go to page 13, example 3. Okay, I'm throwing you guys in the deep end. You guys did do transformations with Mr. Van, right? Okay, good. Of trig. Okay. So we'll do example 3a. All right. So here's what I'd like to do. I like to take a look at this and set that equal to 0 and also set it equal to 2 pi. So what I'm doing is I'm trying to find my new start and ending points. So this is start. Because doesn't the parent function start at 0 for sine, right? X equals 0. And it ends at 2 pi, right? But I'm trying to find my new starting ending points. So 2x equals pi over 3. Ah, geez. X equal pi over 6. So that's where I'm going to start it. So I'm not really using the cloud method. We're using my method, or whatever you might call it. What's the period here, by the way? It's going to be pi because you do 2 pi over b. The b value is 2, so you do 2 pi over 2, which is 1. It's pi. So period's pi. So if I think about it, where is this going to end? It's going to end at 7 pi over 6, right? Because if I solve it, you have 7 pi over 3, so it's going to end at 7 pi over 6. I think it's pretty obvious once you find a new starting point, you know where to end it. It's not that hard. So it's going to end over here. Let me stretch out a bit more and let me erase the other stuff. Okay, and then in between, you have to partition it. What will be right in between these two guys? They're 4 pi over 6. And then, ugh, that's so nasty. I don't like that. I guess you could say 2.5 pi over 6. But if you change that fraction up, what can you, how can you can say it's also 5 pi over 12, if you so desire. You can make all in terms of 12, I suppose. And that would be then, I think 11 pi over 12. Also, I kind of don't care. You have the partitions, you're good enough. Um, where was the vertical shift? So I call that my midline. My midline is y equals 1. So you're going to be, basing the amplitude off that. Okay. And it's sine. So it's going to start on the midline or above it? On it. And amplitude is what? So 1, 2, 3. It's not really doing the cloud method, really. I just kind of sort of just understand my knowledge of trig functions. And then I just do this. And we have to go 3 up, 3 down. Very important. That should go down to here. Okay, I did a terrible job, but I could do better. That's fine. But you get the idea, right? Of how that's graphed. You can always check in Desmos too if you want to verify it. By the way, you could factor out the 2 from here, and that would have been pi over 6. We call it the phase shift or horizontal shift. So I'll show you this in Desmos in a moment. But what you want to be present to is this formula here, which I kind of don't kind of like how that's written. I personally write like this. Y equals A times sine or cosine, bracket B, X minus H. That's how I personally write it. Where H is a horizontal shift, A is vertical shift, B is a horizontal stretch or compression, which impacts period, of course. A is the amplitude, the vertical stretch. Amplitude is like vertical stretch or compression, right? By the way, can it reflect? Yeah, base negative. Totally can reflect. We don't really do horizontal reflections with trigs, so we just don't really mess with that because it's kind of not really necessary to do that. But that's generally what we do. So that's the amplitude. Vertical shift. Horizontal shift. And I'd say period is 2 pi over b. Now, don't worry, we will pump the brakes when we meet again Wednesday. When we start doing graphs of tan, cotan, secant, and cosecant, it's the same principles. It's still involves transformations. But that's where we'll be a little slower. Say, okay, it's shifting this way, it's stretching this way. Don't worry. But I just had to just make sure I'm jogging your memory of the stuff. I don't want to take too long talking about this. It's not the best use of our time. But don't worry, we will talk about these things with the other trig functions when we graph them. I guess I want to show you this in Desmos. So in case you're curious, so what was against y equals 3 sine 3 sine 2x minus pi over 3 plus 1. Now, sometimes it's a little annoying because like, well, I want to see this in terms of pi, right? So go to a little monkey wrench here, and you could totally it's in radians right now. Degrees, obviously, it's messed up. But you totally could just do this. I want to go negative 2 pi to 2 pi and make my step pi over 2. Totally could do that. Now it's a little bit better for us. And we do see, oh, okay. All right. So we see what's going on there. Remember, that was being kind of weird. Was that 2 pi over 3? Yeah, I think so. Yeah, I'm pretty sure it's 2 pi over 3. Yeah, I'm pretty sure. So anyhow, let's keep on moving. One last thing. This is my favorite. Writing the equations from the graph. Here's the deal though. I'm gonna want you guys, I want A to be positive. I want H to be positive. So let's get the K value out of the way. What's my midline? Y equals what? So K is -3. What's our say again? Oh yeah, you could say there's no shift. That's possible. But I want this is what we want. Or actually added instructions. Because I will be very explicit. I'll say, oh, I want like A to be negative or H to be negative. So these are added instructions. What's going to be my amplitude? 2. What's my period? Yep. Okay. So y equals 2 sine bracket -3. So 2 pi over b equals 4. What would b equal, guys? Pi over 2, love it. And I don't have a phase shift. Nope. So you can just write that. That'd be valid. What if it is a cosine? We'll keep the same amplitude, same period, of course, same vertical. The only difference is going to be the h value. Cosine starts over here. So you can do x minus what? There we go, x minus 1, right? Correct. Wait, sorry, say again? No, h is positive. Because the general form is x minus h.
Oh.
Yeah, sorry, no, you threw me. No, I was getting nervous. If like I didn't know. Like, I've been so confident. Like, no, just kidding. No, because it's x minus h is built into the formula. Yeah, sorry. I was thrown for a loop there. Yeah, no, it should be x minus 1. Yep. Yeah, you just kind of look where it starts, so that makes sense. Okay, so that's kind of a quick flyover of trig. So for homework, what I'm gonna have you guys do, I'll tell you the homework I want you guys to do. I'm gonna update Schoology as well. Let's see here. So we'll do 2 through 18 even. '20. So 2 through 18 even. 20. 22. 23. I'm gonna cross off 24 because you guys know it's actually no, I do want to keep 24. I do want to keep it now. Um just trying to think here. 26. 29. 33, 34. And 38. Yeah. So total of 18 questions. Yeah. So these go by pretty fast. So that's gonna be your homework. I'll take a picture of that. I'll post school to it later today. So yeah, that's homework. The solutions I'll post school so you can see them. Yeah, that's pretty much what we'll do. All right.
Wait.